Hey team, Dr. Jay Cordy, and I'm continuing my step-by-step guide to research. And in this video, I'm going to start breaking down the next sort of mini-series, which is a step-by-step guide to quantitative research. So in the previous video, I talked about how to get a research question. How do we develop a research question which is meaningful and feasible and will advance human knowledge? The next step is to create a hypothesis which builds to a theory based on your research question. So you've got to turn your research question into a hypothesis, and your hypothesis should hopefully grow into a theory. Well, so what are theories and hypotheses? Well, they're really just different ends of the same spectrum, and so they can kind of have the same definition. It's an explanation of natural phenomena. And it's quite a short definition, but sometimes when something is so broad, it's worth keeping it short and sweet. Now, this is sort of the definition that you'll see online, and there's a couple of tweaks and changes I'd like to make to it. Well, first of all, let's explain what a phenomenon is. Well, it's facts or situations that are observed or will be observed. And so a lightning strike is a phenomenon, or more people dying following a COVID-19 infection is also a phenomenon, right? So an explanation of those kinds of phenomena. But also I'd like to chuck something else in there, an explanation or a set of explanations, because hypotheses and theories aren't necessarily just one-liners. They can be actually quite big. There's this thing in Alzheimer's called the amyloid hypothesis. It's quite big and complicated. And think about the theory of evolution. There's a lot that goes into the theory of evolution. It's not a simple one-liner. So it's an explanation or a set of explanations that explain facts or situations that are observed in this world, right? From lightning to COVID-19 deaths, right? So that's a hypothesis and a theory. So what's the difference between the two? Well, pretty much just evidence. If there is a huge amount of evidence and almost no conflicting evidence, then we start to call it a theory, right? It becomes the theory of evolution, right? There are multiple lines from multiple fields that all point towards the theory of evolution. And, you know, we're talking thousands, hundreds of thousands of research papers that all support the ideas of the theory of evolution or the theory of global warming, for example. Whereas hypotheses are so early on in the research that maybe there's only evidence around it, like there's no specific evidence for it, but there's evidence around it. Or maybe there's just a little bit of evidence for it, or maybe there's a bit of evidence for it and a bit of evidence against it, and we're still weighing up a couple of hypotheses there before we're willing to settle into something more solid like a theory, right? So that's largely the differences between a hypothesis and a theory, but they're all just really an attempt to explain the world that we live in. Important point here though, you can never prove either, right? You can't prove anything in science. And this is such an important point. And when I read a paper or an assignment by a student and it has the word prove in it, my heart dies a little bit, because it's so important to understand that you can't prove anything. And no matter how sure you are of something, you know, a piece of data might come out of nowhere and kick you in the face and be like, no, that theory that we all thought, it either needs major revision or it's completely not true. And a fun way to talk about this is David Hume, he's a Scottish philosopher. He was a huge proponent and spreader of the idea of this thing called the induction fallacy. And what David Hume said in a Scottish accent was, yo, just because something happens like 1,000,000 times doesn't mean it will happen again the next time. And he actually said that a way more fancy way. He said, it implies no contradiction that the course of nature may change, and then an object seemingly like those which we have experienced may attend with a different or contrary effect. Essentially, he's saying one day we could let go of an apple and it could float up and not go down, right? And so there's no rule that says the laws of nature has to stay the same. They could change, they could flip on their head. But also new data could come in and flip a new theory on its head. And so the induction fallacy is no matter how many times you've observed something or seen something in the past, doesn't mean that it will continue to be observed in that way in the future. No theory is robust enough to survive forever, is kind of what it's saying. And one classic example is called the black swan fallacy. And this is really the induction fallacy all wrapped up into a nice little story. But if you were in Scotland or England in the 18th century and you came up with the hypothesis that all swans are white, you could go to thousands of ponds across all of Europe, and every swan you would see is white. You would collect millions of data points over multiple seasons, observing it again and again and again that all swans are white. So have you proved your theory that all swans are white? Well, no, because you might go to Australia and you would find a black swan and you'd be like, "Struth!" but in a Scottish accent. Yeah, so this is called the black swan fallacy. And it was the idea, no amount of white swans disproves the existence of one black swan, right? You could have 1 billion white swans, there still might be one black swan. And so every theory and every hypothesis could potentially stumble upon new data that falsifies it. Now that sounds like a weird and extreme example, and we can obviously see, if you did count every swan on the globe, you can maybe confirm that all swans are white, for example, but maybe there's swans on Mars or something. It seems like a weird example, but it has happened in science. So let's have a look. Gravity, right? So gravity is objects with mass attract each other. Now we would call this the theory of gravity, but some people call it a law, the law of gravitational attraction. And this was obviously proposed by Isaac Newton. And we have a near infinite amount of evidence for this, right? Every time you've dropped your pencil, every time you've dropped an apple, every time the moon has gone around the earth, every time the earth has gone around the sun, right, has provided evidence to Newton's theory of gravity. And it's the idea that matter just attracts. So heavy matter attracts and is proportional to the mass and the distance, right? Inversely proportional to the distance. And using Isaac Newton's theories, we went to the moon and back. And these images never portray how crazy it is that we went to the moon and back using Isaac Newton's theory of gravity, because this is the actual distance from the Earth, which makes it seem way more terrifying. So ultimately, Newton was a bit of a badass, right? He created these really amazing mathematical models that really explained the world, and every time we dropped an apple, his mathematical models worked. Every time we launched a spaceship, his mathematical models worked. Every time the moon went around the Earth, his mathematical models worked, right? So we had collected an amount of evidence that should have proven that gravity exists, right? But then along came this guy, Albert Einstein, and he said, well, in Isaac Newton's world, time is constant. So 1 second is 1 second. And in Isaac Newton's world, 1 meter is 1 meter. But I don't think that's true. I think mass actually warps space-time and does all this crazy other stuff. And so he proved that, he created a theory that in extreme situations, i.e. with really heavy mass, or really fast speeds, Isaac Newton's physics would break down and his definition of gravity would disappear. Isaac Newton's formulas would stop working, and so all the theory of gravity as proposed by Isaac Newton is in fact wrong, according to Einstein. And they quickly devised a number of ways to test it. There's the orbit of Mercury, but this was the first test, was that Newton believed that light was traveling too quickly to be influenced by gravity, and it was really low mass. And so light should really just zip by in a straight line heavy objects. Whereas Einstein said light travels in the fabric of space-time, and if space-time is bent, then light must bend too. And so essentially they came up with this theory. A way to test their theories is during a solar eclipse, we can look at the sun, and the sun's all blacked out. And under Newton's theory, the stars on the other side of the sun should go dead straight. And under Einstein's theory, the stars that are directly behind the sun, the light from those stars would travel and bend around the sun and hit Earth. And now we will be able to see them, because normally you can't see them because the sun is like too bright. You can't see the stars that are close by the sun, right? But during an eclipse, maybe we'll be able to see the stars as the light from these stars are bent around the gravity of the sun. So does the sun's gravity have a massive effect on the light coming from these stars on the other side? Perfect test. And here's the famous photo, and these stars here should not be visible, but they are, because the light from those stars has bent around the sun, and we can see them during a solar eclipse. So this is a solar eclipse, and here we go. So suddenly Isaac Newton's theory that it survived hundreds of years, 150 years maybe, and had been tested thousands of times through really rigorous tests, has now found some new data, and it's got kicked in the face, and out it goes, right? And so this is the induction fallacy at play, and this is a testament to why you can never prove a theory no amount of dropping apples can prove Isaac Newton's theory of gravity, okay? New data may come along and kick you in the butt. And so the black swan sitting there saying, your attempts to understand this world are futile. The induction fallacy is telling us, hey, you're not going anywhere, buddy. Scientific progress isn't going to happen. But how do we make science work? Because obviously science works. We've cured diseases, we've developed amazing vaccines, we've gone to the moon, we've put up satellites, we've got smartphones that aren't great, but are great. Anyway, so how do we make science work given the induction fallacy and other problems with science? And this is where this guy came along. He's an absolute legend. He's a Jewish philosopher who fled Germany for obvious reasons in the middle of the 20th century. Came to New Zealand, safest place and best place in the world. Whoop, whoop. And there he did some amazing philosophy. And he came across a key idea that virtually all quantitative science lives under this idea. We still need to pursue knowledge to advance humankind. We can't give up with the induction fallacy, philosophical skepticism. Oh boy, it was getting crazy out there. He's like, no, we need a framework in which to build knowledge. And he said, we can't know anything for sure. We can't prove anything. We can't know anything, but we can have theories. We can have theories about this world. And one theory can be better than another theory. So Popper really developed a framework to decide which theory is better than another theory, and how do we develop a good theory or a good hypothesis, which we need to do all of science, right? So that's the whole point of this video. Okay, so he said theories must be falsifiable. You must be able to disprove a theory. And how do you disprove a theory? Well, the theory can only be disproven if it makes predictions. So theories need to make predictions, and then we can do a test to see if their prediction comes true, and then we can falsify that theory or not falsify that theory. And so if a theory makes a prediction, it's falsifiable. So a good theory needs to make predictions, and therefore a good theory is falsifiable. Predictions should tell us useful stuff about how the world should behave. So, there are theories like there's one called the teapot theory, that there's a teapot orbiting this Earth, right? And every ounce of space you look, you don't see a teapot, but that means it could just be in a different part of the space or a different time and space, but there is a teapot orbiting this Earth. That makes a specific prediction that there is a teapot orbiting the Earth, but it's not useful. So it's not a very good theory, and it's very difficult to falsify. You would need to test every speck of dust for thousands of kilometers in the potential orbiting zones of the Earth. But it's not useful, so it doesn't really matter. It's not something we can think about. It's not a good theory because it's not providing utility to us. It's not useful. And the more specific the predictions is, the more useful the theory is, and the more falsifiable a theory is. So vague theories that are still technically falsifiable, but it's not making specific predictions, aren't good theories. They need to make specific predictions, and that will make it more useful. Okay, so let's have a look at a bad theory. So this is one of Elon Musk's. He buys into this theory. There are real philosophers out there that believe this theory, and it's the idea that perhaps we're living in a simulation. The idea goes something like this. If we're all familiar with the game GTA, Grand Theft Auto 1, looks like it's got 20 pixels in it. Grand Theft Auto 2 has a few pixels, but then it gets better. Grand Theft Auto 3, 4, 5, 6. The graphics get better, the characters get better, and the characters aren't scripted anymore. They start generating their own text, their own conversations with the characters, and so on and so forth. Perhaps we're living in GTA 1 million, right? Perhaps we're living inside a computer who's simulating the universe. And coincidentally enough, the simulation looks exactly like our universe. And so there is no difference between our universe and a simulated universe. Now, this isn't creating testable hypotheses. It's not making predictions. There is no way we could falsify it, right? We could travel 13 billion light years out and say, look, we haven't found the edge of this universe. Therefore, we're probably not in a simulation. We've traveled 13 billion years. Are you telling us the simulation is 13 billion light years wide? And they can just go, yep, that's just more simulation, right? So if it's not creating a testable hypothesis, it's not a good theory. Now, it's fun to talk about. It's fun to talk about in your cafe, having a coffee, chat. Are we living in a simulation? Sure. But is it a good scientific theory? No. Is it providing usefulness? No. Is it testable? No. So Karl Popper wouldn't be happy with this theory. Now, another theory to do with Elon Musk is that he is a better fighter than Mark Zuckerberg. That's a reasonable theory. It's at least creating a very specific prediction that he would win in a fight, Elon Musk versus Mark Zuckerberg. Now, we'd need to repeat it to be sure. I recommend 100,000 times. Let's get them fight every day from now on. That would be good. Why not? But that is at least a specific prediction and a testable hypothesis. So it's a reasonable hypothesis. How useful it is, that's a bit questionable. Maybe Karl Popper would give this a distinction rather than a higher distinction when it comes to a theory. Very testable, very specific, not that useful. But it's a reasonable hypothesis. At least we can test it. And so let's talk about it, specificity and prediction, right? So both Isaac Newton's theory of gravity and both Einstein's theory of gravity and time. So here Einstein's clocks are running at different speeds because it's all about relative time dilation, blah, blah, blah. Now, they had different predictions, and then when we looked at the sun, we saw that Einstein's predictions were more accurate than Isaac Newton's predictions. So now we can reject Isaac Newton's theory of gravity and say that there is now more evidence for Einstein's theory of gravity. Now, because of these specific predictions, let me give you an example of how useful that can be. When we sent up satellites to run our GPSs, we need to put very accurate atomic clocks on these. And so these satellites are orbiting the Earth at extreme speeds. Now, Isaac Newton proposes that by being further away from Earth's gravity well, but also by going faster, you end up changing the length of a second from the perspective of those satellites down on Earth, right? And from Earth, the satellite's time is different. And when they initially sent up the rockets with the atomic clocks on to set up our GPS networks, they said, let's just go with Isaac Newton's theories. Let's not take into account for time dilation based on the speeds of these satellites. Well, the satellites immediately got hundreds of kilometers out. The GPS satellites were immediately hundreds of kilometers out because of time dilation. And so, again, Isaac Newton's theories were so useful because they made specific predictions about what would happen with time. Once we incorporated Einstein's theories into these atomic clocks, the GPS system started to work. So Einstein's theory made very specific predictions, and they were incredibly useful, and they tell us about how the world works. So it's a great theory. But guess what? Einstein's theories of gravity and how they work in stretching space-time is not working at the quantum scale. So new data might come in eventually and refute Einstein, and a new theory will come in encompassing both satellite data and stars across the universe data, as well as subatomic particles, right? So even Einstein's theory right now is under threat of going the way of the white swans, all swans are white theory. Now, Karl Popper also said, so sure, you fail to falsify a hypothesis, you fail to falsify a theory. That doesn't mean you have proved it. What have you done? Well, what he argued is that a good theory is constantly being tested, right? Over and over again, it will get new tests and new tests and new tests. And the more times it survives a potential falsification, the more times someone tries to falsify it and fails, the more useful that theory is, the more accurate the predictions the theory is obviously providing. And so therefore, it's worth still having that theory. And another way to think about that is theories are under constant selection pressure of falsification. It's kind of like evolution. All these ideas are springing up that potentially explain the phenomena. They all get tested, and they get tested over and over again. And every generation, some theories die. They get falsified. And only the theories that continue to survive despite attempts to falsify, they keep surviving and keep surviving and keep surviving, are the ones that provide the most usefulness and explain the world the best from our current data. And so when a theory is falsified, a lot of people outside of science point to science and say, haha, your theory got falsified. See how garbage science is. It's not a very good method. It's always falsifying itself. All its beliefs get chucked out of the window every 50 years and everything. Karl Popper says, and we say, That's science working, right? If that's not happening in your system of knowledge acquiring, that means your system of knowledge is stagnated. It's not evolving, right? If it's not constantly falsifying itself and changing and adapting, if it's still got the same beliefs it had 100 years ago, then your system of knowledge acquiring isn't working as well as science. The whole point is that our theories fail and new theories supersede it. And then we get a more accurate prediction and understanding of the world and how the world will behave in the future. So Newton was wrong, but that's science working. That's great. That's fantastic. Okay. And that's the evolution of knowledge under science. Okay. So here we go. Step 1, develop your research question. We talked about that. It should build off the existing literature and the existing momentum of the literature and take that next step to acquire knowledge. We need to create a hypothesis, which builds into a theory as more evidence supports it. And this theory or hypothesis should make specific and useful predictions about the world. Step 3, collect data, and this is important, that attempts to falsify your theory/hypothesis, right? So next up, we need to actually test it. We need to go out and collect data. This is quantitative science here. We need to go collect numbers that are going to attempt to falsify our theory or hypothesis. And that's going to come up in the next video. What data? What data should we collect? How do we collect data? What kinds of data are available to collect to attempt to falsify our hypotheses?